Air within a piston cylinder assembly is initially at a pressure of 30 psi. Temperature is 510. Volume is 6 cubic feet. It's going to be compressed isentropically, keyword there, to a final volume of 1.2 cubic feet. We're going to assume ideal gas model. There's K. And we want to determine the mass, final pressure, final temperature, and work. Now, let's look at our TS diagram. Notice it says isentropically. Yeah, remember, this is S. At state 1, we've got a pressure of 30 psi, and our temperature is 510. Now, if it's isentropic, that means state 2, and it's compressed, we are going to go up to here like that. Remember, isentropic means no change in S, so there's got to be a vertical line here. So let's just say up here we've got some pressure 2 and then T2. We don't know what those are yet. Now part A, we want to find mass. This is ideal gas, so we can write that mass is P1 V1 over RT1. So let's take our values here. We've got 30 psi. So you've got that. We need to convert over to feet squared, so do that conversion there. Let's see, volume is going to be 6 cubic feet. Actually, that should be, and then after that we're going to put that over RT. R, we have 1545 over 28.97. And really, you could find the constant value for that instead of finding it all the time. I just always find it. And then the temperature here is going to be 510. It's already in degrees Rankine. That saves us some time. We don't have to convert. Now, if we look at everything, all of our units are going to cancel out to what they should. This all goes away. That cancels 2 of these. This last one is canceled with this. Pound force goes away. We're left with pounds here. That gives us 0.953 pounds. There's our mass of the air. Part B, we want to find final pressure. This is isentropic. We got ideal gas, so we can write P2 equals P1 times V1 over V2. Raise that to the power of K. That'll give us a P2 of 30 psi times 6 cubic feet over 1.2 cubic feet. Raise that to a power of 1.4. That's going to give us 285.55 psi. Alright, so there's your second pressure right there. So pressure is increased quite a bit there. Now let's find temperature. That relationship here will be T2 equals T1 times V1 over V2. Now you got K minus 1 as your exponent. Plug in your values. 510 degrees Rankine for T1 times 6 over 1.2. 0.4 ends up being the exponent. That's going to give you a T2 of 970.9 degrees Rankine. Notice your temperature also went up. And D. D, we want to find work. For this one, we've got our energy balance equation. Alright, so delta U plus KE plus delta PE equals work minus W. Q is going to go away, because remember, isentropic means adiabatic, no heat transfer, those two go away. And this is regular internal energy. We want to change that over. Work is going to be negative delta U. We could say that is equal to negative M times CV times T2 minus T1, because this is an ideal gas. Remember, CV is R over K minus 1. So this means work is negative M times R over K minus 1 of T2 minus T1. Now plug in your values. So you're going to get negative 0.953 pounds. That's what we had for mass. And then you need R over K minus 1. For R, you're going to have 1.986 over 28.97. Put that over K minus 1. That's 1.4 minus 1. Units be BTU per pound degree Rankine. Now let's multiply by the temperature change. So we get 970.9 minus 510. Those are both degrees Rankine. Look at your units. Pounds go away. Degrees Rankine go away, so you're left with BTU, so that checks out. Your work then is going to be negative 75.3 pounds. That negative indicates that you had to have some sort of energy due to work transferred into the system to make that compression happen. Alright, so that's what you get for that one.